All right, so we hit literally 10:30. I'd like to call everybody's attention. So you don't know me, my name is David Stanford, and I'm an emeritus professor now at the University of Western Ontario, or as it's better known nowadays, Western University. We have an interesting session of free talks, but just before we jump into it, a bit of a plug to make you think when you see me today about CanQ, because CanQ, the doing conference that we have in Canada every August, is being held this year on the 21st and 22nd of August, the Thursday and Friday, the full week before Labor Day. And it's going to be hosted by the business school, which has got very deep pockets, so I'm sure it'll be an enjoyable experience. And London is very welcome here. From the airport, there's a direct shuttle that goes to London. If you prefer, there's a train express that comes downtown, and there are good train connections, about 4 trains per day. And usually have a very interesting program, but it's a little bit like this. It's a fairly intimate conference. So if you see me today and you want to talk about CanQ, I'll be happy to talk with you about it. And if you're in applied probability, that's how wide we cast the net. Okay, enough about that. So if you, well, I think everybody must be familiar with at least the idea of the Erlang C and Erlang C systems for sizing communications devices, server pools, and what have you. So I'm quite looking forward to our first talk, which Amir is going to be giving, and it's on the subject of solving Erlang C systems with customer abandonment and server unavailability using it. Amir, please.
Thank you very much. This project is done with myself, Arash Askari, who is a PhD student at the University of Alberta, and Said Samidawi, who's a professor there. And Arash was going to do this presentation. That's why his name is in the program. But he now turned out that his paper got accepted for MSOM, which is going to start as of tomorrow in the UK. So he decided to go there, and then how I ended up here presenting this work. The project started with a data set that we had for a call center of an organization that serves vulnerable people. We were playing with the data to see if we can model it with any of the standard queuing models, but we did not have that much of success. Mainly, one of the main features of the data was that they had very long wait times. So on average, people had to wait around 2 hours to get to an agent. And because of that long wait time, the abandonment was 60%. And because of these features, we thought that, okay, Erlang A should work well, at least well enough, but it was not the case. And after doing some investigation, we noticed that the problem is agent unavailability, meaning that agents serve the callers, but some of them, after each call, they just become unavailable because they need to take notes, they need to do some follow-up work, so they cannot accept new callers for a period of time, and then they come back on the lines. And basically, this violated the main assumption that Erlang A and other common queuing models have, and that is if we schedule servers, they are always available. Either they are serving a customer or they are available. And this system violated that significantly, and that's why we were not getting good results. If I want to show you a schematic view of the system, we have customer arrival here. They are impatient customers with rate gamma. They leave the system if their patience time is lower than their wait time. If they get to service, they receive their service and then they leave the system. The service rate is mu for everyone. Gamma and mu can be different rates. The key is here. Once a service is completed, then the server becomes unavailable with probability 1 minus alpha, or remains available with probability of alpha. If it becomes unavailable, then with rate C, it goes back to the pool of available servers. So this is the basically main difference to standard Erlang A system. Now I'm going to show some of the results from the end, using the end model of this work, just to motivate why we need to have a model that explicitly takes into account the server unavailability. Here, there are some performance measures, and these parameters are for that realistic system. So that is for the real system that I talked about. Here, these performance measures calculated using Erlang A, and these are the same performance measures using the QBD model that I will explain. And if we take this to be the real kind of values, because it has more detail, it models more details of the system, we can see that Erlang A is underestimating significantly. And for example, for this specific one, average wait time in the queue, Erlang A gives half a minute, but QBD gives 8.5 minutes and so on. So there's a very big difference if we miss that aspect of the system, server unavailability. Okay, how do we model the system, or as a QBD? Level is the number of customers in the system. Face is the number of available servers, and it allows us to calculate all other required parameters of the system, including those in the queue and so on. Now here is the notation for the queue system, for the queue matrix that we use. We use upward sign to indicate rates of going one level up, this right left arrow to rates of staying in the same level, and downward arrow for rates of going one level down. And this is a level dependent QBD because remember we have that impatience, abandonment. The higher the number of customers in the system, the higher the abandonment rate. So this is level dependent. The death rate depends on how many customers we have in the system. Some more notations, we use pi L to show it's a vector of steady state probabilities. Each of these, they are vectors by themselves. They include the faces. We know that for a QBD, for a level dependent QBD, these vectors pi, they are connected to each other through the matrix that we call the rate matrix, and it's going to be a focus for most of my talk today, and I'll give more information about this R matrix. Yesterday, Doug also talked about that. And this standard system of equations, PQ equal to 0, and adding all those all steady state probabilities adding to 1, they are just standard set of equations that because of this recursion, this system can be written in the form of these two equations that you can see they depend on R. Basically, it means that if we can calculate R, we can calculate pi 0 here, and then from there we can calculate all other steady state probabilities. So the bottleneck is kind of calculating this rate matrix. But why is this difficult or challenging to calculate the R matrix? For a typical LDQBD, the number of levels is infinite, and the calculation of R matrix includes infinite sums. So we need to somehow truncate that system to be able to approximate that R, and that is kind of problem that we usually face. Common approaches are so that they truncate the system either using a heuristic or even just arbitrarily, and then that's how they calculate the R matrix, and then they obtain the steady state probabilities. But unfortunately, they also usually don't provide bounds, so we don't know how accurate our estimations are. A couple of years ago, I was involved with a project to address this issue, which was instead of truncating the system arbitrarily or heuristically, let's let the system to design, or the algorithm to decide where should that truncation level be. And that way, we can also guarantee some bounds on the steady state probabilities. So that way, we can calculate the steady state probabilities with any desired accuracy that we want. And that paper is published in IJOC, and a part of this presentation is going to be about that, because we need some basics from that, and then we'll focus on this system that we are dealing with to see how we can apply that algorithm to this new system. Okay, let me first provide or explain the very nice physical interpretation that the R matrix has. Before talking about that, let me first define LP excursion, okay? And LP excursion is a sample path that starts, let's say my P is equal to 2. I am in level P, level L and 2, and excursion starts when my sample path goes from this to level L plus 1, and as long as I am in one of these higher levels, L plus 1 and above, I'm still in my excursion until for the first time I go back to level L. Okay, that's excursion L and P. The P and P prime element of the R matrix is the time that I spend in, let's say my P prime is 3. The time that I spend in L plus 1 and 3 during that excursion for the unit of time that I had spent in level L and 2. So that is that interpretation of the P prime element of RL, the rate matrix of level L. Okay, any questions about that? Because that is basically the key for calculating bounds on the R matrix. Now let's see how we can use that definition to calculate each element of the rate matrix. And this formula here is motivated by a paper which was published in 2006, but that was for a level independent system. We upgraded that, or we adopted that for a level dependent system, and then we'll use this to calculate our bounds. Okay, let's see what are these components of this equation. I am in level L and 2. In order to start my excursion, I need to go to level L plus 1. Okay. For now, let's assume that there is only one path to do that. With the red probability, I go to level L plus 1. Then my excursion starts. I am in these higher states. During that, sometimes I meet this green stage, which is L plus 1 and 3. The expected number of visits is this blue. So now I have calculated if I am in L and 2, the probability of going up multiplied by the expected number of visiting this green state. Now I'm multiplying that, the expected time, that each time that I'm visiting this green, on average, for how long do I stay there? That's this value here. Divided, so the numerator multiplied by this is the total time spent in this green inside my excursion, divided by the expected time I spent in my initial state, L and 2. So the whole thing gives me the expected time in L plus 1 and 3 per unit of time I spent in L and 2. So that is basically what my R of P and P prime is. If you look at this equation, I can calculate an upper bound and lower bound for each element of R by overcounting and undercounting this expected number of times, right? If I can achieve that, basically I will have bounds on my R matrix. Okay, let's do that. Let's assume that I have a taboo level. Let's call that M. My taboo level is 4. So L plus 4 is my taboo level. So 4 is kind of my limit for that. In order to undercount, I assume that the system starts from L plus 1 and 2, but now I'm only focusing on sample paths that never reach all the way up to taboo. So I'm just considering a subset of sample paths. So this way I'm undercounting. And imagine that if I keep increasing m, when m goes to infinity, basically I'm calculating all, I'm considering all sample paths. And this way, by limiting m to a number, I'm only calculating a lower bound. This is my undercounting. For overcounting, anytime that I hit the taboo level, I bring the system back to my state of interest, which is L plus 1 and 3. That way I am overcounting. Again, if I increase m to infinity, this will never have, this overcounting will never happen, and I will get my regular or true R. So that's the whole idea about undercounting and overcounting. And what is my m? We increase m so much that the element-wise difference between the lower bound and upper bound is at least epsilon r, which is a desired accuracy for my R. And please note that whatever I have described so far has got nothing to do with my system. So it can be applied to any level dependent and level independent system. Okay, now I have my bounds. For the R matrix, I can plug that into the equation that I showed you earlier to calculate upper bound and lower bound for my unnormalized steady state probabilities. That's what I'm showing with X. X underbar is under S, lower bar, lower limit, and X over bar is my upper limit for unnormalized. So now the key is, how am I going to convert these bounds to steady state probabilities? I need to calculate bounds on my normalizing factor as well. If I divide my unnormalized with a normalizing factor, I'll get my steady state probabilities. To calculate my lower bound on C, normalizing factor, I simply add up my unnormalized lower bounds. Upper bound is a little bit trickier. For upper bound up to level L, I calculate, let's say it is the level that I have stopped going forward. Up to level L, I have the lower bound and upper bound for unnormalized. The sum of upper bounds gives me the first component of my upper bound on my C. So how am I going to calculate bound the rest of the part that basically I'm truncating? This part is going to be system specific. If for my system, I can find a level above which the R matrix element-wise becomes non-increasing, then this X over bar is an upper bound on all these remaining X's, right? And therefore, I can just easily calculate these sums. That is what we do, and that way we get a lower bound and upper bound on steady state probabilities, and basically we have achieved our goal. But how do we calculate that L tau for the system that I just described with server unavailability? Let's pick a phase P and another phase P prime. The probability of going from LP to L plus 1 P prime going up, that probability multiplied by the probability of coming down, again, from any state to any state. Going up, coming down, we can prove that there is a level above which this up and down probability becomes non-increasing. And that level is the level that I can use to establish this summation. We proved that. And this inequality has to hold for any pair of P and P prime. Okay, once we have that, that overbound on C can be calculated, so we are done. Okay, now I have explained how we solve the QBD of our system of interest, but now let's look at some managerial insights that we have gotten. And we have many plots, but for the sake of time, and I also thought these are more interesting, so that's why I'm focusing on these only. One very interesting application for this model we noticed is when we are talking about staffing algorithms. We know that there are some standard, I would say, staffing algorithms like square root staffing, and which is for MMC, Erlang A version of that, which is by Garnett, Mandelbaum, and Raymond. That is for Erlang A, and they're all based on diffusion approximation of the system. Okay, if we use those approximations on this. And here, on the x-axis, we have delay target probabilities. On the y-axis, we have the number of agents that we need to achieve these target probabilities based on each of those algorithms. This green and blue, they are the number of servers required based on those kind of standard algorithms. But this dotted line is the one that we are getting from our QBD. And you can see that there is a significant difference between them, indicating that if we don't capture server unavailability, then we may end up with this type of understaffing. Here, I should say that, especially with the GMR algorithm, if this is instead of service rate, if we tweak the parameters, we can get this line. But the thing is, how we should adjust that. If you adjust that correctly, and we know that only now that we have this, so that kind of undermines and at the same time supports. So I would love to get your feedback on that. How we can justify that this is still valuable, because if we use GMR with those tweaked parameters, we get very close results to this. But again, how would we have known that if we did not have this, right? So that's one thing. Another thing is, which I find even more interesting, is now we have technologies of note-taking and things like that, right? So should the management invest on those technologies or not? We are trying to answer that question with this. We have number of agents. We have target probability of delay. And these are cases, the rate at which my servers become available after going unavailable. If I can increase that by using, let's say, ChatGPT. ChatGPT is taking notes. I don't need to take notes, so I can go back to serve faster. So I am increasing my KC. By increasing KC, how much should I increase that? So much that instead of 20 servers, now I can have, let's say, 16 servers. Is the saving of decreasing number of servers by 4, would that just justify investing in that note-taking technology? That's another thing that we are getting from this. Yeah, that's all I had. As I said, there are a few other plots, but I found these more interesting. And now I would love to hear your feedback on this, especially your thoughts on the issue that I raised here. Thank you very much.